I think the last time I was in a position like this where there was lights in my face, I was on stage in high school in Hello Dolly. So I promise not to break into song, but it is, you know, it's not terribly intimidating to have these lights in my face because I've been there once before. Today I was asked to come and talk to you about dealing with the intermittency of renewables. And I've put quotes around that, dealing with the intermittency of renewables, and I'll get to the point of that later in my talk. But in doing that, I come with a very unique perspective because I'm an academic at the Australian National University first and foremost. And I work there as a lecturer. I work with students. I work in the academic research space. And one of the things I've been doing is really trying to push the envelope in terms of getting academic research out of the university and into the real world. It's something I'm very passionate about. And that's where my role in Solcast has shown up. And that was, you know, in the introduction a little bit. But one of the things that gets a bit tricky there is I work as the CTO in this company we formed, and I'm an academic, and, well, I really start to bend rules and break things. So it's always important to make sure that, you know, I've got both those hats that I wear, and I'm going to try to wear them both today. What makes that really fun, though, is it actually gets us hands-on with industry really effectively, and we can take some things that we build in the university and get them out in the real world, and I'm going to talk to you about that today. So from my perspective, when we start talking about the intermittency of renewables, graphics like this come to mind, right? So we have Australian rooftop solar and storage markets just, you know, really growing very, very quickly. With 6 gigawatts of rooftop solar installed in Australia now, another 6 gigawatts projected by 2020, and with the large-term projections for large solar looking to be in the 3 to 4 gigawatt space for total installed capacity, which in my engagement with solar farms and people putting these farms in and planning them, we might blow right past that. We are getting to penetration levels of solar in this market that are quite unprecedented and in reality quite challenging for some reasons that I'll enumerate today. And if we look at our own ENA roadmap, they've got this plot here where they plot some of this growth on an upward trajectory for both rooftop solar and battery storage. And just for reference, I've put the total peak NEM demand on there from the heat waves we had this past summer, and also the peak New South Wales demand for the 10th of February, just as some reference for the total gigawatts of capacity for solar and the amount of power output it would be generating under clear, bright sunshine. This is really fascinating to me. Where we're headed with our networks and markets is really exciting, and really solar is driving this, and storage is right behind. When I look at a graph like this and I think about where we're going in the future, the question of intermittency naturally comes up. And this is an area that I've been focusing with my academic research for the past several years. It's now becoming a real-world issue. We need to deploy solutions for intermittency. It's a challenge for both wind and solar, although today I will focus on solar because that's my area of expertise. And the word intermittency, people use it a bit interchangeably to mean whatever they might like, but there's actually a formal definition for it in the academic space, and that is seeing that for example, with the sun, that it varies in intensity throughout the day. It comes up, it's up above your head at noon, sets in the evening, it's unavailable at night. The second component of that is the interruption, the variability induced by cloud cover. And so these are the two components of intermittency. One of those things we can model exceptionally well. We know when the sun comes up, we can model the availability of solar radiation at the Earth's surface to within 1% accuracy. So we know where the sun's going to be available and when. The big question is those clouds, and that's the tricky part. And when it comes to intermittency and it comes to variability, it creates real challenge. Real challenge that I really enjoy engaging with because my background is actually as an atmospheric science and a meteorologist. And in my former research career, I actually studied convective storms. So what we have here is an example from the 17th of February where we had some convective storms form in eastern New South Wales on the East Coast Trough and then move over the population centers of New South Wales. And if you look at the rooftop PV actuals from the AEMO, a solar forecasting tool for rooftop PV called ACEPS2, we see that we effectively go from 800 megawatts of rooftop PV to around 200 megawatts of rooftop PV generation over the span of really about 2 hours. So this is effectively taking an entire generator, large coal generator, off the market in terms of meeting supply and demand. And issues and challenges like this with fast-moving, fast-changing cloud cover, one of the key challenges here, are happening on a weekly basis in our energy markets. Maybe not at that severity, but they're certainly causing those impacts already. And this is with that 6 gigawatts of rooftop solar mark. Add another 6 gigawatts. What is this going to look like? And with the key issue here with this fast-moving, fast-changing cloud cover is we need to start being able to predict when that's going to happen. The other issue that we have with solar is specific to rooftop solar, the behind-the-meter solar, as it's called in many other markets, and that's a lack of visibility. There's a total lack, near total lack, of real-time feedback, historical actuals, or near-term future predictions for rooftop solar PV systems. They're not reporting in real time, the vast majority of them. So we have this visibility problem. And that means particularly in the LV networks, for our distribution networks, it's very hard to do the investigative work to understand where voltage problems may be coming from. You might do some guessing that it's solar, but can you prove it? Can you attribute it? Without real detailed data, that's exceptionally difficult to do. So one of the things that I've seen over the last few years of my work was a real need for detailed solar information to get down into our LV networks. And that's where this ARENA project that was introduced today, and I'm not quite sure what happened to my graphic there with the ARENA coming in front of there, but this is supposed to say, Confronting the Intermittency Challenge. I guess ARENA really wanted to know, you to know that they're funding me, and they are, so thanks for that, guys. It's about a $4 million project now. There's been a bit more funding coming its way, and what we're doing is we're deploying operational distributed PV forecasting for distribution networks. And what we're actually doing is different than what any other market in the world has done with solar forecasting, because we're mapping those forecasts to the grid. So I'll explain what I mean a bit more in this upcoming slide here when I talk about the data that we're getting. And what we're also doing with this is we're taking the IP out of the university, and we're each year putting new IP into operations within Solcast, that company. So this is where it starts to get tricky with wearing both of those hats. But the real motivation here is if we waited to the end of 2019 when this project was done, you all would have blown right past us and hacked together your own solutions. We want to make sure that we're meeting the needs, we're really responsive to what industry needs, and we get this stuff out there. And for me, the primary objective here on a personal mission that I've turned into my team's mission and Solcast's mission is to demonstrably raise the allowable penetrations of solar PV in our grid. And that is not something we can do on our own. We must do that by partnering with all of you in this audience. But we do see the technology that we're bringing to market as a key enabler of being able to do that. So in order to do that, we need to confront these two problems, the lack of visibility, particularly in behind-the-meter solar, and the fast-moving, fast-changing cloud cover. Let's look at problem number one. So problem number one is this lack of visibility. How do we solve that? Well, one of the key issues is actually a lack of detailed PV metadata, capacity, location, characteristics of these PV systems. And we do have some reporting from the Clean Energy Regulator, but there's some problems with it. We miss the above 100 kilowatt level of installed PV market, which is growing very quickly. It's one of the fastest growing segments of rooftop PV, the rooftop PV market. And we end up without getting data that's actually network centric. So what we do is we go work with these distribution network partners. We figure out where the installed behind the meter solar PV is, and we group that information by distribution network asset. What distribution transformer are these PV systems connected to? What feeder do they map back to? What zone substation do they map back to? And how does that go up to the transmission network level? The reason this is important is that if we're going to provide solutions, if we're going to enable solutions for solar-based intermittency in the LV network, in the transmission level networks, we need to know the solar variability ahead of time by the PV systems that are installed at each of those network assets. So we're actually mapping the solar variability to the grid. And in order to do that, we've actually had to partner with these, it's now 11 DNSPs. Thank you very much. I think Jay Stein's here from Core City Power. Thanks, guys, for joining. We have now got 11 of these DNSPs on board. If you don't see your logo up there, we're happy to involve you. There's no barriers on our end. We're taking the data, working with these distribution networks to get that data and remove that opacity and then return back to them visibility of the embedded generators, the embedded PV generators on their network. And so what they'll actually get is access to these forecasts in real time. The second thing that we're doing to help remove this lack of visibility is we're partnered with Fronius and SMA. So we're actually getting them to build an API service, so kind of monitor that active grid edge directly and give us access to that. so that we can real-time monitor PV systems. And this is on the order of tens of thousands of PV systems of data that are coming into us. And so what we need to do with this data is not only check and see if our forecasts are lining up with what we expect from these PV systems to actually be producing, but we actually have to learn how to take in this massive amount of data, quality control it, use it in an intelligent fashion. And what we can start to do with that once we do some value add is we can actually start to look at our second tool that I'm going to introduce, which is a satellite-based system, and actually dynamically tune our forecasts. And that's really the bleeding edge of some of this tech. So problem number 2 is the fast-moving, fast-changing cloud cover. You know where all the PV systems are installed. You know them by the different network assets. You're monitoring some real PV system data in real time so that you know if your simulations are on par and you have some historical data to work with. But how do you actually enable predictive technology? There's a lot of companies that say they can do solar forecasting. But if you do not monitor cloud cover and track cloud cover and forecast cloud cover, you're not really forecasting, because what you won't do is you will not predict a cloud coming ahead of time. You'll respond rather than being proactive to a cloud arriving. So our technology, what we do is we use something called the Himawari 8 satellite. It's an amazing piece of technology, and it's the first of a next-generation fleet of satellites that are geostationary weather satellites that are going up around the world. Most recently, GOES-R launched over the United States, will be live later this year. It's equivalent to the satellite I'm about to describe. And what it does is it images clouds at 1 kilometer resolution and updates every 10 minutes. So what this fantastic resolution is doing is it's a game changer in terms of data, in terms of monitoring and predicting what's going to happen at the active grid edge. Because at 1 kilometer resolution, we're tracking individual clouds explicitly. We're seeing where they move every 10 minutes, and we're able to then predict where they're going to be in the future, as well as with the multiple channels in the satellite, some fusion with weather models, also estimate how thick they are. And so what you see in the right-hand side of this image is actually a decomposition of different cloud layers that allow us to determine a cloud opacity. With a cloud opacity determinant, then we can use radiation modeling to model the available radiation at the Earth's surface and the current motion of the clouds to project them forward in the future. And that's what you see there on the left is an example forecast of us predicting where clouds will move in the near future. And we do that at 10-minute increments. So doing all that sounds great. We can marry those two sources of data up, but we still haven't got to the point where we can enable the networks to do anything about it. That's a very tricky thing. And this is actually at the heart of a broader discussion about where APIs and cloud-based services will go in terms of interacting with utilities. So this is another thing that we are very interested in figuring out. And our first stab at it is actually producing an API, an application programming interface. And what we're doing is we're actually building up these solar forecasts and grouping them by the distribution network assets. And we're building an API service that will allow our users, these DNSPs, to actually be able to say, I would like to see the solar forecast behind this zone substation at that distribution transformer. And not just the forecast, but the recent actuals. And looking back into history and seeing what the valid satellite scan, the actual snapshot of where clouds were at the exact time that we measured them, we can use that to build a historical picture of what PV variability has done on the network as well. So we can enable network planning, we can enable network operations, and what we're doing with this system is we're building up a prototype API actually based on a suggestion from one of the teams we're working on this with at Ergon. They said, why don't you make an API? Let's try that out. And so we're going for it. That's the first thing we're going to do. But the thing that we're going to be exploring after this API is actually trying to directly integrate with some of these distribution management systems. And we're having some very productive conversations on that front. Because it's going to be very important to get this detailed solar variability and forecasting into those load flow modeling tools that many of you use. We actually saw a good demonstration of that from the Ergon slide from Michelle just before. We need to actually be able to figure out what these networks are going to do and get the solar variability and forecasts into those network-based tools. Otherwise, we'll continue to be blind for solar, and this API service might just be a nice to have, nice thing to look at. We've put out a little demo where we actually do this, and you can see this live on the Solcast webpage, where we're doing this at the connection point level with solar PV installed in South Australia. Just as many of the other speakers have hinted, we see South Australia as the forefront of this conversation where solutions are going to be coming into the picture in the near term with the large amount of investment opportunities that this has attracted. One of the key things I see is the dealing with intermittency problem is actually an opportunity for energy storage technologies. And one of the reasons we did this is we actually were able to say, we know where the PV systems are installed at the connection point level. Let's put together a model for that and actually model and forecast the variability in real time as a demonstration. And this type of access, this type of API level access is something that we'll be able to do across all of those participating network partners and be able to give a full-scale API where we could have these network assets be mapped to where the solar variability is going to be and actually operated with that API to match it up with solar variability. Now, I've talked a bit about the cool things that I'm doing personally, but I think it's really important to use this opportunity to look back at the big picture. So I want to tie this into the transformation roadmap that ENA has recently released. I personally think that this document is a great point for us to focus a lot of our energy and conversation, and it's not just because they gave me a talk today. So looking into some of these key areas from their summary, one of the things that is a key area of focus is this intelligent networks and markets issue that we need to engage and solve. DER interoperability, enhanced system monitoring, DER energy resource maps, feeder hosting analysis, active network management. This is something that we are directly trying to confront with this API service to enable some of this type of analysis, particularly being able to map solar variability back down to feeders, etc. And so one of the things that we're trying to confront here are those two key problems: the lack of visibility, the fast-moving, fast-changing cloud cover. But when you start to actually look at what solar forecasts can do, it's not just about distribution networks. This is actually a technology that can enable consumers. If a consumer knows that it's going to be cloudy tomorrow, they can make different choices today. If a consumer knows that cloud cover is going to show up during their peak tariff and that their battery is not fully charged, they might want to curtail their demand. Or alternatively, the platforms which are servicing these customers might also want that information. And so actually, when I look at storage, I see storage as largely a charge-discharge based question that is somewhat tied back to solar variability. So if you want to know when to charge your battery or discharge your battery, you will also need to know how brightly the sun is going to shine and where and when. Here's another one that's pretty interesting: solar forecast for system security. So this is actually a forecast that we issued for Broken Hill Solar Farm on the 10th of February, which if anybody is here from Osgrid, they'll acutely remember, was during this heat wave event when there was a forecast lack of reserve, 310 megawatts of load shedding about to be put out in New South Wales. And during that window, there was actually about a 50% drop in power output from Broken Hill Solar Farm because of a rapidly moving, fast-changing cloud cover condition, cumulus cloud deck field, that we actually are imaging there in the left-hand side. So we have the ability to see these clouds, forecast them in the future, and in fact, we were actually, on the Solcast side, able to see that event happening 2 hours ahead of time. So when it comes to managing demand and supply balance in tight situations, solar forecasts are becoming increasingly important, particularly when we're talking about 3 to 4 gigawatts of large-scale solar farms. And I think the other thing that ties this in quite nicely is some of the discussion we've heard today, whether it was about Sandy or Debbie, in terms of these tropical cyclones or ex-tropical cyclones. Meteorology is continually becoming interrelated very closely with the network management and storage dispatch. So we know we're going to go into situations where there's going to be adverse weather. We're going to want to have our systems charged and ready to go to have backup power. So it's this interesting union of meteorological data and forecasting and energy storage, I think, that extends more broadly than just beyond solar forecasting. It's exceptionally important to start to provide easily accessible solar data to Australian companies in terms of being able to map opportunities and take advantage of them. So past, present, and future high-resolution solar data actually enables us to do better planning and network management. And I really like this idea about orchestration as a term. We've heard it used in a couple different ways, whether that's working together, coordination, the teamwork. There's another term that was mentioned earlier. I can't remember it off the top of my head. But this whole idea of using all these different assets very intelligently, orchestration of the grid, as ENA has been using the term, is, I think, going to become increasingly dependent on when and where the sun will shine and how brightly. And that's information that we're working to make very easily accessible to industry and researchers. And I think there's abundant opportunities via things like the AER's Demand Management Incentive Scheme to actually take advantage of solar variability knowledge to avoid network upgrades and further expense. So the real thing that I would like to have all of you take away today is, in the past, we've referred to intermittency as a challenge, as a problem. I would like you to walk away viewing intermittency as opportunity, because intermittency, particularly in solar variability, and solar asset historical performance, future performance, real-time performance is going to be a key part of orchestrating, planning, all of these distributed energy resources that will be being added to our grid. And the more we can map it, understand it, and forecast it, the more effectively we can take advantage of the opportunity that intermittency puts out there. So the real thing that I see as being important is, let's stop thinking about it as dealing with intermittency and instead using intermittency and knowledge of intermittency as the new opportunity. The obstacle is the way, so to speak. And I'll close off by saying, and my slides have been totally mangled, so thank you for your patience. I'm not letting it upset me. This transformation roadmap, I really feel that all it takes for us to pull this off is some collegiality, some teamwork. Some of us are competitors, but all of us are Australians. And I think that this is really important to think about teaming up for a, what I'll say, solar-powered future. You can insert what you'd like there, but really a future based on a promising, abundant supply of energy. And if we break one or two things on the way, I think that's a good thing, but I'm a disruptive startup guy, and I'm allowed to say that. It is the active grid session, after all. Thanks very much for your attention.